Okay, so what we just did with the Maxwell-Boltzmann speed distribution probably seems like a punch to the face because it's just kind of out of left field. So I wanted to refocus the class and kind of, after we've done that, great, it's a bunch of math. Who cares? Why should we care? Let me just walk through this really quick. So the average kinetic energy, and by that I mean translational kinetic energy, would be k bar, which is the average of this function, which is 1/2 mv squared. Well, 1/2 and m don't need to be averaged. They're just the mass of the molecule and some number. So notice this is v squared bar. I want to be clear about this. V squared bar is not necessarily V bar squared. The order of where you put the bar matters here. So we're taking the average of V squared. What do I mean by that? That's the expectation value of V squared. That would be the integral of V squared f of V. When you do all that junk, you get this result. Okay? If you take the square root of that, you get VRMS. All right, cool. Now, if we let E internal, the energy of a single gas molecule, be purely translational, notice we would get, when we plug this in, 3/2 k Boltzmann, the m's drop out, you get 3/2 k Boltzmann T for just one molecule. If you have n of them in a gas, so if you have n molecules, we get this 3/2, which we could write in this way. F over 2, where F is degrees of freedom, all right? And so the internal energy is the degrees of freedom times 1/2 k Boltzmann T. And this actually holds whether you're doing diatomic gas or whatever have you. Well, the definition of specific heat, molar specific heat, kind of a misnomer because it's not really heat, it's some constant that relates to heat, is given by this equation, 1 over the number of moles times the derivative with respect to temperature. Now, notice we get this F over 2R, which is something I quoted. This is the result that we're going to want to be using over and over, and so this is kind of the more important part. I do expect you to know how to do the mathematics of the Maxwell-Boltzmann speed distribution for a test. I've discussed that already in the previous video, but I just wanted to point out, if you're wondering, how in the heck did they get the specific molar heat relating to this weird degrees of freedom? It comes from this equipartition theorem, where for each degree of freedom, you're going to get a 1/2 k Boltzmann T associated with the internal energy. To be clear, internal energy will also include all the other stuff like the intermolecular bonding energy and things like that, but we're going to ignore that, all right? And so, in particular from a monatomic gas, that would also hold. I do want to mention one other thing. I derived this same result here using the ideal gas law on page 79. So if you're curious, and literally just talking about gas molecules bouncing back and forth, you'll see this in every textbook as well. So you can read about this, derive average kinetic energy using ideal gas law, and you can do a web search for that. I just wanted to point out, I didn't pull this out of thin air. Essentially, we could derive that from the Maxwell speed distribution, and that seems like enough. It's the main takeaway I wanted you to get.